So now I don't remember exactly where we were in, but the whole point we were making here was we have no way to branch. We have no way to do like an if. If some condition, do this, otherwise do that, right? Now, it could be, there are a number of ways we can go about doing this. When I say branch, really, I don't mean like it's like an if then else, or something like where there's like mutually exclusive execution, right? All I really care is that we've got some ability to branch. I mean, for all I know, the branching could be something like this, which is effectively a conditioned loop, right? Run this and, but the whole point I'm making is we have no way to branch. We are recording, yes. Okay. And then, but like, if you think about a jump, because we do have a jump instruction, but it's a jump always. So no matter what, it's always jumping, which we used in that counting program where we just always incremented by 1 and outputted the result. Great. But there's some logic there that maybe like the jump can work, because like here's the idea of like the program I have for checking less than 10. Load the contents of f, which is, who cares, some arbitrary number. I just put a question mark here, some number, right? Who cares? We would change that if we wanted to check a certain number. And then we jump to address if it's less than 10. What address do we jump to for? 0, 1, 2, 3, 4. If it's not less than 10, carry on. So we only jump, the idea here is like we only jump if the condition is true. And the condition here is like less than 10. So if we magically somehow know if a number is less than 10, we output 0 because that's D, right here. D is output, unsigned. The value at that address, D, E, F, that's D. Cool. And then we halt. But if we jump to 4, 0, 1, 2, 3, 4, we output DE, which is a 1, and then halt. There. That's like a exclusive OR thing. Now in this particular example, I showed you that we effectively branched and then ended, and we stopped. And we talked about how actually some people hate this type of programming. Remember we talked about this? It's coming back to me now. Where like, oh, you have 2 halts. Really, you shouldn't have 2 halts. You should like come back and only ever have 1 exit. Fine, we could do that. No big deal. Unfortunately, we have no way to do a condition. Now, which condition do we want to check? Do we want a condition to check if a number is less than 10? No, that's rather silly. But we could do things like, okay, check if a number is equal to 0 or less than 0. That's actually not too hard to check. If a number is equal to 0, then we can check equality pretty easily, because if I want to check if 2 numbers are equal, I can calculate their difference. And if their difference is 0, they're equal. If I want to know if a number is less than or greater than, I can say like, okay, take the difference. Is the difference negative? Is it not negative? I can know if it's like less than or greater than or equal to, right? So I now really you could do this with any number, right? You don't have to do it with 0, but 0 is a nice, 0 makes a lot of sense to me because we're pretty happy with 0. So we'll put our focus around 0. So we can put our conditions around there. And we're actually going to add a third condition. So we're going to create a condition for if a number is equal, a number is less than 0. And we're going to add a third condition that'll just check like, okay, did the carry bit go high? Because we only have 8 bits, right? Meaning we can only count up to 255. So maybe if we do some sort of calculation and we go beyond its range, maybe knowing if we go beyond the range might be valuable in some way. So we'll have that as well. And then there's this like, technically speaking, really for the system to be like complete, all we actually need is one condition. If it has the ability to branch based on one condition, we can do anything. It's just we would have to like fix things programmatically, but that's a bit of a pain in the butt, so we're gonna have a few more. Remember how I said like you want to check if a number is less than 0? Well, you can keep decreasing, and if you ever pass 0, suddenly programmatically, like software can make up for the deficiency in like the hardware or the system's ability. It's an intrinsic ability. Like, right? Do you remember that? Yeah. Okay, cool. All right. And then, okay, yes, if you go look at your general depiction of an ALU, you see something like this. The two numbers, A, B, the result. But there's all this like side effect crap. Okay, the opcode, okay, fine. That specifies which operation we're going to do. Do we want to add them? Do we want to multiply them? Do we want to subtract them? Do we want to do and? Whatever. That specifies the operator that this ALU is going to do. But we see this status in, status out. This is that side effect stuff. Apparently this produces two outputs. Yeah, one main output and one side effect. A status. The status that we're going to deal with is, was the result of the operation a 0? Was the result of the operation a negative number, or was that significant bit high, which we're really using to check if something's negative? Did it result in a carry? Those are the statuses. So we'll know if something like, ooh, well, let's remember that we just resulted in a 0, for example. Cool? If you remember, in the labs, we built like comparators, right? And we made use of the comparator thing in, I think, in an assignment. I told you you can use a comparator or something, right? So there was the comparator. Now, the comparator wasn't really like a status flag. The comparator really wasn't part of the ALU. But you can actually check conditions like otherwise. So the strategy that we're going to use for keeping track of like 0, negative, carry bit, those like cases for our conditions, the strategy we're going to use to keep track of it is one of many possible strategies, one of many that are actually implemented in hardware. It's a common one. It's a relatively simple one to understand. But there are more sophisticated ways to deal with conditions in your code, like what we were doing in the lab, or at least what we were working towards in the lab. We never really got there, but I was kind of introducing it. All right. And if you go to the digitals, it's not a built-in component, but it does provide a circuit for an ALU that you can actually import into your design, and it's got a fancy little thing that looks like this. We've got A, B, opcode, I guess a carry in, a Y for the output, and 3 flags. These are the statuses. Here it's not showing it as one output, it's 3 separate outputs, but same idea. All that really matters is there's some status that comes out of this. So the ALU that is within digital actually kind of has the same idea that we're working towards. There's no coincidence there. Now, I didn't design it to match digital. I designed it to match what's typical, and digital designed to match what is typical. And you know what? For the sake of some fun, desktop, where do I put digital? Digital, does anyone see it? Desktop? Nope, not documents. Desktop, digital, examples. I think it's under processors, ALU, a regular old one. And you can see, I mean, we've looked at this ALU before, right? What do we do? Well, each of these particular operations always is being calculated no matter what. So the output signal here is always the result of each of these operations. And the opcode that goes in, by the way, these are these like little like tunnels or whatever they call them. This is a way to, as soon as you label one, if they have the same label, they're just magically connected. Yeah, but no, we don't, that leads to bad design. So it's appropriate in some cases, like here, fine, right? But like, I don't know what would have been so bad about just like connecting them, but whatever. Basically, the opcode is a multiplexer to select which output we actually care about. I know a lot of people in here in labs and whatnot, and to be clear, this is entirely fine. There's nothing wrong with doing this. Arguably, it's an over-engineered solution. I saw people kind of like muscle that the inputs, based on the opcode, the inputs would map to these, and the outputs where really you only need to map, like you can calculate all of them and only care about the one. It doesn't matter. Is it clear what I mean? Is it not clear what I mean? Do you not know what I mean? You only really care, like this is a perfectly fine design. They're all calculated. Each one of these is always the result of whatever these are. I just only want to output the specific one I care about as specified by the opcode. I saw people also kind of mapping the inputs to the operators based on the opcode. Entirely over-engineered, an unnecessary thing. Nothing wrong with it. Maybe it's better, I don't know, but maybe it saves electricity, who knows. But it requires more hardware and more logic in the hardware. And you'll notice these are the, now this is pretty cheesy if you ask me. They use a comparator to check if something's 0. I think that's pretty lame. But there's the 3 signals coming out for the statuses. Cool. Status flags. So checking if a value is 0 is a matter of checking if all the bits are 0, right? How do you know if a number is 0? If all the bits are 0. Pretty easy. So this can be done several ways. To me, I think a NOR makes the most sense, right? Like think about like an OR. OR is true whenever everything, like imagine I've got like an A and B. This is obviously only for, what am I doing? This is obviously for only 2 bits, but of course you know that this, or it doesn't matter, you can apply OR to however many bits we want. If any of them are high, OR 0, 0, 0, 1, 1, 0, 1, 1. Obviously only 2 bits. We can make 8 bits here. I'm not drawing that table. That'd be 256 rows. Forget it. But they would, all of those rows would be 1 except the one where it's all zeros. And you look at that and be like, well, that's not what I want. I want it to be the opposite of that. Okay, NOR. You just, you know. To me, NOR makes the most sense. I saw people doing it with NANDs. Great, cool, whatever. Yeah, it's entirely fine. Or no, knotted inputted ANDs. That's what they were doing, right? So nodding the input and then entirely fine. We know from those Boolean operators way back at the beginning of the semester, it's all equivalent, right? You can mix and match however you want. Use whatever makes the most sense for you. To me, I liked NOR. So think of NOR operator truth table, yeah. Checking if a number is negative is a little tricky because it requires one to know if the integer is signed or not. It also requires us to know if, like, how big our numbers are, like how many bits, how wide they are. So if it's a signed integer, you look at the most significant bit. If it's a 1, well, it's negative, right? That's always true. Now, we got to be careful because people will be like, oh, so it's a signed bit. Yes and no, because it would be like a sign. It wasn't quite a signed bit, but it effectively is. If it's an unsigned integer, the value can't be negative, right? So how can our hardware know if it's an unsigned or signed integer? Well, the hardware we have, it can't. And you might think, oh, no. No, that just makes it your problem, the programmer, to know this stuff. In the same way that, like, here's an encoding of 0s and 1s. What does it mean? I don't know. You tell me. I have to know what is that information. Am I decoding that as an integer, as a character? Is it a signed integer? I don't know. That's up to the programmer. That's not the hardware's fault. It's up to the programmer. Okay? That's not a deficiency of the system. It's just, it is what it is. So yeah, it's the responsibility of the programmer to know if the data is signed. As a system, it doesn't know. Yeah, there we go. Okay. So all that we could do is check that like most significant bit. If it's a 1, and we know that we have a signed integer, well, then it's negative. But really, you'll often see, like even in that digital ALU, they call it like negative, right? And all they're doing here, by the way, if you look closely, it's taking the output. You did this in the labs effectively, right? It's taking the output, but it's branching it off here, and it's got this like splitter. And this is a weird thing you haven't seen, but basically we're only taking that 15th bit. By the way, this is clearly a 16-bit ALU, right? 0 through 15. It's looking at 15th bit. If it's high, it's saying it's negative. Now, I don't like that. I think that's bad because that assumes that it's a signed integer. It might not be. So with this, all I could ever say is like the significant bit. Is the most significant bit a 1 or a 0? Then me as the programmer has to go like, okay, that does mean, okay, it's a sign. Okay, yeah. You had a question or comment? No? Cool. That's just me being overly picky perhaps. I think most people would be like, yeah, it's the negative thing. But, you know, it kind of actually depends, but fine. I think it's important though because, we're learning about this stuff. So yeah, then the programmer, knowing the context in which it's using the system, can determine if it's negative or not. Finally, knowing if an operation resulted in an overflow, a carry, whatever we want to call it, is a matter of checking the carry signal from the adder, right? So we have an adder. If we look at our ALU, we had that carry out. We could look at just like the gate configuration of an adder, right? We remember a full adder configuration of gates and whatnot, and we did have that carry out. But we generalized it, we abstracted it to that little box in our system, right? Because it's a little nicer to look at, and it has that little carry out. How do we know if the operation we did caused a carry? Look at the carry bit. If it's high, it caused a carry. Now, I mentioned this last time. I mentioned this last time. The way that we're going to do this is going to be based on really like this design here. We're not going to check if a number is 0. We are. But like the spirit of what we're going to do is I'm not going to be like, is the number in the A register 0? Is the number in the A register negative? We could do that. But if I were to say, is the number in the A register, did it cause an overflow? That's not really a fair question. If I look at the bit pattern 0, 1, 0, 1, 0, 1, 0, 1, and I ask, did it cause an overflow? You have no idea. An overflow would have had to have been caused by an operation. In fact, we could move all of that like status information, 0, negative, carry. We could move all the logic of that to the ALU. But the question becomes, did the result of the last operation cause a carry, cause a negative number, cause a 0? Did it produce these things? So I'm not going to look at a number in the A register and make a decision about it. I'm going to look at the result of the ALU as it's being outputted and remember, hey, did it cause these things? Cool? That's the idea we're going for. So, yeah, okay, checking OR, checking that high signal, there. So how could we check? Well, here's an easy one for checking 0. You take all the bits. I don't know, I always kind of find it annoying that this isn't nice and evenly separated with the, I wish it was consistent because it makes for some obnoxious designs you'll see in a moment. But I've got an 8-bit number, it's coming in. If we OR them all and not the result, and it's a 1, they were all zeros. Remember, and also if we knotted the inputs and then did an AND, that would also be, yeah. And then finally, that high significant bit. If it's high, well, high. So I'm going to call these things flags. Okay, I've got the Z flag. Z for what? 0. S for what? No. S for what? I just ranted about this. Significant, the significant bit, which conveniently is also sign, right? So I know, I'm just being a jerk. And how do we check that carry one? Well, that one's just kind of silly. Imagine it's attached to the ALU, the adder, right? I know, whatever. Imagine it's connected to the adder. Well, it would just be hooked up to the adder's carry bit, right? So there we go. I like how you're all like, haha, yeah. Yeah, it's pretty silly. So that's how we can check this stuff. And now I know we did this in the labs, but it's, we're reminding ourselves of this. Now, we've got a bit of a, okay. Imagine I've got an adder, okay? And this adder, it's got an A and a B. These are coming from the A and B registers, right? And it's got the ability to do subtraction, fine, whatever. So here's what I would do. Now, realistically, we know that in our ALU design, or sorry, in our ESAP, in our system design, the output here, this output went back to the bus. I'm not drawing that here. Okay, this goes back to the bus, whatever. But I'm also going to, like there's a branch here. This goes back to the bus. But I'm also going to observe that output and do, okay, was it 0? Was it high? And also, was the carry high? That's the idea. Note, It's not so much that I want the output to go from here to here. No, I want the output to go back to the bus, but I'm observing the output. That's what this is. This is my observation of the output, okay? And this is what I mean about, like, it's kind of annoying that this isn't evenly. See what I mean? It causes that annoying little, like, jog. Cool. Now, what do I say here? All right, so the output of the ALU would typically be sent back to the bus, but the output, okay. So what we want to do is, like, the goal is to know, is the result of the last arithmetic operation, whether it was addition or subtraction, is the result of that operation, did it cause any of the status signals to change? But think about a particular, like, we've got a bit of a design conundrum with our system. Let me check here. I want to see, do I have this as an example? Desktop. I think this might be better shown with a clear example. Conditions, control logic with flags, control, adder, flags, register, flags. Is it this one? No. This one? No, don't look at this. Don't look at this. Control logic with flag. No, don't look at this either. No. Okay, I clearly don't have it. All right, that's fine. So, here, can I? There. Delete, there. There. Okay. Run. Perfect. So right now I'm adding 0 and 0, and of course the Z flag is high. We see that, right? Yeah? If I do like 1 and 1, well, okay, none of that is there, right? But if I do subtraction, I should get a 0. Now you might notice, oh, wait a minute, the carry flag went high? Yeah, because this is tangential to the point I want to make, but I want to, like, make sure you're not left going like, what? That makes no sense. No, it makes perfect sense. It makes perfect sense as a consequence of two's complement arithmetic and how we kind of like cheese the bit width, or the width of each like word of each bit pattern to work. What is the bit pattern for 1? What is the bit pattern for 1? But we're doing -1, which means we actually do 2's complement before it goes into the adder. What is the bit pattern for -1? Right? So this is 1 and -1, but it is also 1 and 255. If you add these two numbers together, what do you get? You get, oh, 0 carry the 1, 0 carry the 1, 0, 0, 0, 0, 0, 0, 1. That is 0 if you ignore this, and that is 0 if you ignore this, right? But the carry bit is there. So this is, you might say, uh-oh. No, that's just how it is what it is. This isn't a hardware issue. This is but that's just how 2's complement works. All right? All right. So it's one of those things we got, keep in the back of our minds. All right, so there we go. 0. If we do 1, -2. Okay, cool. There we go. Okay, now we did 1 minus 3. We see that is high, right? Cool. And let's just do some really. Let's not do subtraction. Nope. Why is that? Oh, because the significant, right. I was like, why is it saying it's negative? It's not. It's just letting me know that the most significant bit is in fact high. Anyways. So cool. All right, there we go. These are all going. But, so here's the bit of a problem we have. So let's say, for example, I have one. Is this clock not hooked up? Oh, no, it's not, because it's not needed. 1, and we do subtraction. And we look at this, and we go like, perfect. 1 minus 1 does result in 0. And that's exactly what we see there. Perfect. But think about our addition and subtraction instructions. Okay? The first part of that instruction is fetch. Fine. Let's say, okay, this is subtraction. We do our fetch. Then we output from, we output from the ALU. And where does it go? You should know this. Where do we put the output? Think of the instruction, the microcode steps for subtraction. We output from the adder. Where do we put the output from the adder? In the A register. Meaning this would immediately change to this. Now, the last instruction that we just did, was the last instruction move the contents of the adder to, or like move the contents from the adder to the A register? Not really. That was a microcode instruction. That was a microcode step of the bigger instruction of subtraction. So the result of the last subtraction I cared about, the one I said, save this result into the A register, the result of that was a 0. Did produce a 0. But when that instruction, the full instruction finishes, as far as this hardware is concerned, it wasn't. Do you see the problem? If it's not clear, ask now. It's caused because the ALU is always outputting the result of the A and B register. If I say subtract, I want to know what the value from that adder is now, not after I change what's in the A register. I change what's in the A register, this changes, the status signals are going to change, but I wanted to know what the status signals were when I said do the addition or do the subtraction. Is it clear? So it's at this moment, do subtraction. Oh, I just want to get this value. I want to know what was the status right now. But the full instruction would modify A to become 0, and this changes. Crap. Now, what do we do? What have we always done when there's data that we want to keep track of? You use a register. So we will use a register to latch in the status signals when we care about them. So we'll just have a register where we enable it when we need to enable it, and we disable it at every other time. Yeah? Yeah. Registers. What a tool, right? So, yeah, so the goal is to know if the last arithmetic operation performed caused any of the status signals to change. However, the adder is always outputting a value based on the contents of A and B. This is true even when addition subtraction is not intentionally being performed. So like, I could just be putting data into A and B, and those status signals are going to change, but I only care about them at a specific moment, right? I could be putting data into A and B for whatever reason I want, and these signals will change. But I only care about what the signals are at a very specific moment. So Consider the steps the system performs when calculating 5 minus 5. Load 5. Oh, I've got an issue there. An extra backtick. Load 5 in A, 5 in a B, set subtraction signal. At this instant, the status signal is 0. The overflow will also be high. That's just 2's complement. Put the value from the ALU into A. At this instance, the status flag for 0 will be high. This is because the adder always will, oh, I have this backwards, will not be high. This is because the adder always calculates the sum difference of the values. Therefore, since the ALU is outputting -5, the 0 flag will be low, but the significant sign flag will be high. So obviously, we've got a problem. The second calculation was an unintentional and a consequence of the design of the system. Okay, I've just got some typos in here I got to fix. All right, so here is me showing 5 minus 5. That's what we want. But the next instant, it would go to this, because the 0 would go into here from A. Yeah? Yeah. So the status signals are always changing, but these signals are to be known at very specific times. The result of the last operation. The last operation we actually really cared about. If I wanted to do 5 minus 5, that's what I cared about. I didn't care about 5 minus 5, and oh, also there was this like inconsequential, or this resulting 0 minus 5, right? Like that was not what I cared about. That was just a consequence of the fact that A is an accumulator. It's always storing some value. In other words, there needs to be a way to preserve the status flag value at this, when the specific operation is done, a register. We'll call this the flag register. Raise your hand if you've come to my office and you've seen my breadboard computer behind me, right? That is what my design there has been missing. I've been meaning to build it for like the past 5 years. I just haven't, like it's been in that state for a long time. And I'm like, oh yeah, every day I walk in, I'm like, one day I'll add a little register. It really wouldn't take very long. I'm just lazy. So yeah, that's what it's missing. And because we don't have a way to like check a condition, we can't do a branch. And so my system is not complete. The key is to carefully control when the register's inputs, the status flag signals are actually stored. Only enable the flag register to store the signal when performing the actual addition and subtraction we care about. So here, if this was my steps, I would be like, at this instant, okay, set the subtraction, okay? So I would set the subtraction signal. I would output from the ALU. I would input to the A register, and I would enable the flag register. That's what I would do. Then, everything else is disabled. It's latched. It's saved. We're good. Below is an example of an adder with the logic of the status flag. Hold on. In all other cases, the value being output by the adder component doesn't matter. Yeah, so when the flags register is not enabled, those signals, the values, like whether or not the value coming out of the adder is a 0, or the sign bit is high, or carry is high, it doesn't matter if the flag register is not enabled. So with this, all condition checks are based on the last arithmetic operation performed. All status checks, whatever, the 0, significant sign, carry conditions. Below is an example of that design, the one that I quickly, let's go back, modified. There, that's what it's supposed to look like. So now, really what I would want, if I wanted to do 1 minus 1, right? I would enable the flag register, clock pulse, then this could change all at once. But we can see that, like, okay, the result of the ALU of the 0 minus 1, it's not 0. But the thing I actually cared about, it was 0. Yeah? And the fact that this is high doesn't matter because this flag register is not enabled. You'll notice that, like, how many bits is this flag register? 3, right? The least significant, I guess, based on my design, is 0, sign, significant. 0, significant, carry. Why is it that order? Because I drew it that way. It could have been another order. It doesn't matter. That's not really what's important. But yeah, each of those bits has a different meaning, though. We're storing them in the same register. If you really wanted, if you're like, no, I don't like this. I don't like that we're kind of combining this into like 3 bits and they all actually have separate meaning. Like they're grouped, they're logically similar. They're all like these condition, these status things. If you really wanted, you could do 3 1-bit registers to be like each register, this is the Z flag register. Fine, whatever. If you really wanted, you could do that. But you know, I just think it kind of makes sense to group it together. Any questions about that? So the whole point of this is we have a register to latch those status values when we actually care about them. Cool? Questions, thoughts, concerns, comments? All right. Thank you very much.